Swayam Prabha. Digital India. Educated India.
Welcome. So we are in the last lecture of the module 2, where in the last class we have just introduced the Rayleigh-Ritz method. In this lecture I will try to show you two examples of the Rayleigh-Ritz method. So here first I will just briefly recap and then so here the main focus will be the solving some problem. So that we can understand this Rayleigh-Ritz method properly. So let us start with a simple so first let us do some recap so that we can understand. So here we have we have learned Rayleigh-Ritz method. So the basic approximation of the Rayleigh-Ritz method is this. So B of phi I, phi j equals to L of phi I minus B of so let me write it in terms of summation so that you can understand. So that is j equals to 1 to n B of phi I phi j into Cj equals to L of phi I minus B of phi I into phi 0. So the phi 0 is just to satisfy the non-homogeneous boundary condition, and then phi i's are the weight function. So our approximation of suppose u is my field variable, then this approximation will look like this. So j equals to 1 to n Cj phi j x, and then we'll have this phi 0. So now suppose we want to solve some problem in this thing. So now one of the important thing here is that weight functions will be linearly independent, and then because this will lead to system of a simultaneous linear system of equation. So this will leads to simultaneous linear system of equation, and that will actually has to be invertible to find out the unique solution of the Ritz coefficient Cj's. Now to do that, let us take some example. Let us take some differential equations. So let us take some general differential equation. So let us take some this equation. So ddx of 1 plus x du dx equals to 0. Okay, and this is for x 1 to 0, and there is a boundary condition. The boundary condition, let us take u0 equals to 0 and u1 equals to 1. So this is the boundary condition. So now if I approximate or construct its weak form, so the first step is to construct its weak form. So weak form will be considered some weight function w. So weight function w. So this is the integral statement will be 0 to 1 w into minus d dx of 1 plus x into du dx into dx. So this has to be 0. So now if I do integration by parts of this equation with the weight function w, then it will look like simply this. So 0 to 1. So this minus sign will result in positive plus sign here. So this will be dw dx into 1 plus x into du dx into dx. Then there will be boundary term. So boundary term will be your w into 1 plus x du dx. So this has to be at x equals to 0, x equals to 1. So this is my simple weak form because there is no right hand side, so that's why it will be 0. So now the main requirement for the this weight function is that it should satisfy the admissibility condition. So that means w has to be 0. So this term will essentially be 0. So we won't have this term, right? So this is the weak form. But if you remember now, if I substitute this approximation, that is the approximation of u, then now let us follow the Rayleigh-Ritz method. Rayleigh-Ritz method or Rayleigh-Ritz approximation. So to do that, let us take my approximation for ux is something like this: Cj phi j plus phi 0. So j equals to 1 to n. Now I'll choose some particular n. Now this, if I do that, then this weak form will also give me a term in the right hand side. I will come to that. So here if I choose phi j is my approximation function, and weight function is also if I choose weight function w here in the previous expression, w as phi I, then my weak form, this weak form will look like this. So integral 0 to 1 d phi j phi I dx into 1 plus x and d phi j dx into dx. So this quantity multiplied by Cj summation over j equals to 1 to n, and then I will have another term due to phi 0, so which is essentially my integral 0 to L or 0 to 1 d phi I dx into 1 plus x into your approximation for this. So that is my phi 0. So this is d phi 0 by d phi 0 by dx. So this is into dx. So this term will also be there. So naturally this will be my bilinear form, and this will be my linear form here. So if I just substitute this quantity here, now let us now represent it. So this is nothing but the summation of j equals to 1 to n b of phi I phi j into Cj equals to L of phi I. So now here I equals to 1 to n. So this will give me a n equation. So from that n equation I can find out Cj's. So now the main important part is how to choose this phi 0 and phi j's and phi i's. So first of all, phi i's has to satisfy the homogeneous boundary condition. So what is the boundary condition of the problem given? The boundary condition of the problem given is u0 equals to 0 and u1 equals to 1. So now my phi I at x equals to 0 has to be 0 and phi j or phi I at x equals to 1 has to be 0. So this is the condition for the admissibility. Now to choose this admissibility condition, what kind of function I should choose? So and also you see that there is a non-homogeneous boundary condition. So naturally my phi 0 I have to choose. So phi 0 x has to phi 0 means has to be 0. Phi 0 has to be 0 here and phi 0 1 has to be 1 here. So this is the requirement. So the choosing this thing, the phi 0, if functions that has to satisfy these two conditions, the simple choice of phi 0 is x. So if I choose phi 0 equals to x, then this satisfies these two conditions. Now choosing this condition, so how to choose this function? So now phi i's, if I choose suppose phi 1 is my x into 1 minus x. So this will satisfy my both the condition. So similarly phi 2, if I choose x square 1 minus x. So like this I can choose. So both of these function satisfies the admissibility condition or the homogeneous boundary condition. Now finally my approximation, let us consider in the previous expression n equals to 2. So my approximation of ux is something like this. So c1 into phi 1 plus c2 into phi 2 plus phi 0. So now c1 I don't know, I have to find out. So c1 x into 1 minus x plus c2 into x into 1 minus x square into 1 minus x plus x. So this is my approximation. The whole idea of the Rayleigh-Ritz method is to find out this c1 and c2. Now so why I choose like this? So can I choose phi zeros or phi 1 and phi 2 different function? Yes, you can choose. But suppose phi 1 I choose x square into 1 minus x and phi 2 is x cube into 1 minus x. Then what will happen? So if you look carefully, this is x square minus x cube, this is x cube minus x to the power 4. So in my approximation there will be no linear term on the x. So when I choose my phi 1 as x into x minus x into 1 minus x, I consider the linear term. So choice of this type is not preferable because we are doing approximation for we are finding out approximating solution or approximate solution. So this will not be my complete polynomial or the complete polynomial approximation of u. So naturally this type of approximation is not good because it will not represent the complete polynomial in the approximating solution or approximate solution. So Now, so that's why we always prefer to choose the complete polynomial because it represents the whole gamut of the solution or whole polynomial expression within the approximate solution. Now, once we do this, so once we finalize our approximation and choice of this phi 0 and phi i's, then I can just put this equation. So let us now find out. So first of all, let us first find out the bilinear form. So b ij, so bij's will do, and then we will do the i's. So the matrix form of this will two term will, if you expand this expression, so this expression if you expand, so b11, b12, b21, so b21 is essentially b12 because it's a symmetric bilinear form, and so this is b22, and then this will be my c1 and c2. So now there will be right hand side also f1 and f2. So now how to find out this b11? So the finding out b11 is essentially integral 0 to L. So first let us see what is my bilinear form. My bilinear form is this. So d phi I, so d phi 1 dx into 1 plus x into d phi j, so j is 1 here, so d phi x phi 1 dx into dx. So this is my b11. So now what is my L1? So L1 is my d integral 0 to L d phi 1 by dx into 1 plus x into d phi 0 by dx. So d phi 0 is x here. So now this is the L1, or essentially the F1. So Li's are Fi's. So let us choose this is F1. So now to evaluate this integral, we know my phi 1 is this. So d phi 1 by dx is, so d phi 1 by dx is simply x 1 minus x minus x, so 1 minus 2x. So naturally my b11 will be integral 0 to 1 plus x into 1 minus 2x whole square dx. So this is my b11. So if you integrate b11, then you will find out what is the solution for the b11, what is the coefficient for b11. So b11 if you integrate, then you will get b11 half. So similarly L1 or F1 is integral 0 to L d phi 1 by dx is 1 minus 2x into 1 plus x, and phi 0 is x, phi 0 we choose x, so this is 1, so this is my dx. So here if I take that, then I think there will be a minus sign here because we are representing it in this form. So this is minus f1. So now here it will be a minus. So now this if we integrate, so this will be 1 by 6. So now similarly if I choose b12, so b12 will be integral 0 to L or 0 to 1 d phi 1 by dx into 1 plus x into d phi 2 by dx into dx. So this will be my B12. Now what is phi 2? Phi 2 is my this. So x square into 1 minus x. So we can calculate d phi 2 by dx and then substitute and find out what is the this B12. So if I do that, then this will come. This we can simply find out what is B11 and B12. So B12 I have calculated earlier, so that is 17 by 60. So now similarly B21 or B12, since bilinear form is symmetric, we can find out 0 to 1 d phi 2 by dx into 1 plus x into d phi 1 by dx into dx is equals to 17 by 60. So similarly I can find out B22. B22 also we can find out. So B22 is integral 0 to 1 d phi 2 by dx and 1 plus x into d phi 2 by dx into dx. So this will lead to my 7 by 30. So you can check whether this is correct or not. Similarly F2 we can find out, so which is integral 0 to 1 plus x into d phi 2 by dx into d phi 0 by dx. See, d phi 0 by dx is constant, so essentially we know that is integral 0 to 1 plus x into d phi 2 by dx into 1 dx. So this will result me 1 by 12. So now my equation looks like this. So b of b into c equals to f. So this if I write, so my coefficients I can just put it half, then 17 by 60, then this is also 17 by 60, and then this is 7 by 30. So this equals to C1 and C2, and this will be equals to 1 by 6 and 1 by 12. So if I now solve this, then C1 and C2 will be 55 by 131 and C2 is minus 20 by 131. So once I solve this problem, I get the approximation for u. So u of x is 55 by 131 x into 1 minus x plus, so there is a minus here, so minus 20 by 131 into your x square phi 2, so x square into 1 minus x plus x. So this is my approximate solution. So now we also find out the can find out the exact solution of this problem. So u exact for this case is your log of 1 plus x by log 2. So this is my exact solution. So now if I increase my exact solution, so if I increase my approximation, so that means if I increase n as so this is for n equals to 2 solution. So now if I increase my n equals to 3, then this solution will be modified. So u approximate will be more closer to u exact. so it will be more closer to u exact, and so on. So if I plot now, suppose if I plot this thing, so as I increase order of the in the polynomial, so it is increased, and then ux solution, if I try to increase, then at a particular point I can find out that if this is my exact solution, then if this is my exact solution, an approximate solution will start from somewhere here, suppose. So it is slowly will go to this. So these are my different n solutions. So this is this, and so different solution. So this is known as the convergence. So we'll come to that later again. So what is the main idea is here, that you essentially change the order of approximation, that means order of the polynomial you change, then you are more closer to the exact solution. So this is one example. Another example, we can see it from our this thing. So structural mechanics example let us consider. So let us consider a simply simple cantilever beam with a moment m0. So now this is suppose this cantilever beam is loaded with q0 force, then I is my constant. Now what is the boundary condition for this problem? So I know this is a fixed end, so this is w equals to 0 is 0, wl equals to 0, and then here w dash l or dw dx. So that is, so since this is Euler-Bernoulli beam theory, so dw dx is slope, so dw dx is 0. So slope and displacement is 0 at this particular x equals to 0. And what is the boundary condition at this point? You see moment is given. So naturally ei d2w by dx2 is m0. So what is the other boundary condition? Other boundary condition is shear force has to be 0 here. So ddx of ei d2w by dx2 has to be 0. So if I take ei constant, that is ei d cube w by dx cube is 0. So this is the boundary condition of the problem. Now what is the weak form? So again I have to approximate my w. So w is I can approximate like this. Let us say C1 phi 1 and C2 phi 2. Okay, now then again I have to choose phi 0. So what is the phi 0 needs to satisfy? So here I am considering n equals to 2 like in the previous example. So what is my phi 0? So phi 0, you see that homogeneous boundary conditions are homogeneous. So naturally I can just simply say my phi 0 is 0 because all the boundary condition that is this is 0. So this is the only Dirichlet boundary condition I have in the system. Now what is my phi 1 and phi 2? So phi 1 has to be, you see, phi 1 has to be phi i's. Let me write phi i's. So phi i's at x equals to 0 has to be 0. So this is one of the condition, and phi I dash that is phi I dash has to be 0 at x equals to 0. So what is phi I dash? That is d phi I by dx at x equals to 0. So this is the requirement of the weight function. So now my phi i's, what is the simple choice for phi i's? So suppose I choose my phi 1 is x square. So it satisfies this condition, that homogeneous admissibility condition. So now similarly phi 2, if I take x cube, I can also find out that this satisfies the admissibility condition. Now similarly, if I have phi 1 and phi x, then my W approximation for n equals to 2 is this. So C1 x squared plus C2 x cube. So now main objective is to find out C1 and C2. So how to find out C1 and C2? First let us see what is my weak form. So let us find out Bij. So that is 0 to L EI by 2, not EI by 2. So that is my phi I is my weight function. So d2 phi I dx2 into EI d2 phi j dx2 into dx. And what is my linear form or this thing? So this is L of phi I. So that is L of I. Let me write it in this way. So that is equals to 0 to L Q0 into phi I dx, and then we'll have the boundary term due to, because this is a natural boundary condition is not homogeneous, natural boundary condition has this term. So naturally phi I of L, so at L it will be, and this will be M0, right, because this will have this thing, right? No, phi I dash, so because the weak form requires 2 times differentiation, so phi I dash. So if that is the that if I write it again, so that is Q0 phi I dx plus d phi I dx at x equals to L into M0. So this is slope. Slope is conjugate to the moment, right? So this is my linear form. Now similar to that, I have found out phi I and phi j's. So once we know phi i's and phi j's, then I can just substitute these into these to compute B11. So B11 I can compute. So suppose 0 to L d2 phi 1 by dx2 and EI d2 phi j or phi 1 by dx2 into dx. So phi 1 is my x square. So naturally, what is my d phi 1 by dx? D phi 1 by dx is 2x, and d2 phi 1 by dx2 is my 2. So this is very simple. So integral 2 EI by into 2 dx. So naturally 4 EI by L, right? So this will 4 EI into L. So similarly I can find out my L1. So L1 is my integral Q0 0 to L Q0 phi 1 is x square. So phi 1 okay, let me write it so that you understand. Phi 1 dx plus d phi dx d phi 1 by dx at x equals to L into M0. So this is nothing but integral 0 to L Q0 phi 1 is my x square, so Q0 x square by dx plus d phi 1 by dx, which is essentially your 2x. So 2x means 2L into M0. So this is the term. Now this term I can evaluate. So if I evaluate this term, this is nothing but Q0 L cube by 3 plus 2 M0 L. So similarly I can find out B22. So B22 I can find out, and B12 I can find out. So B12 seems to be 6L square EI, and B22 seems to be 12L cube EI. So the terms are very familiar to us, because we know from the stiffness matrix of a beam that 2EI by L square, 4 EI by L, 12 EI by L cube, these terms we are familiar with. And L2 that will looks like that 1/4 Q0 L to the power 4 plus 3 M0 L square. So you can just do it on your own to integrate with phi 2 as my excess cube. So this, if we substitute, then we get this. So finally my equation is now B11. So let me write directly what is the equation. So this is EI I can take common, so that is 4L 6L square, and then 6L square 12L cube into C1 C2 that is equals to Q0 L cube by 12. If I take common, then this is 4 and 3L plus there will be an M0 term, so M0L 2 and 3, right? So this equation we can solve it to find out C1 and C2. If I solve for C1 and C2, then C1 seems to be 5Q0 L square plus 12 M0 divided by 24 EI, and then C2 is essentially minus Q0L by 12 EI. So now my approximate solution, which is W approximate solution, is C1 phi 1 plus C2 phi 2. So this equation I can write that 5Q0 L square plus 12 M0 divided by 24 EI minus, sorry, here I have to, this is C1, then I have to put x1 phi 1 is x square, then minus Q0 L by 12 EI x cube. So this is my approximate solution. But if you know the exact solution of the problem, the exact solution we can easily find out for this kind of problem. Now if you do it for the n equals to 3, then you will see that you would reach the exact solution. For instance, if I choose phi 1 as x square, phi 2 as x cube, and phi 3 is my x to the power 4, then we get the exact solution. So again, this validates, so if I just, this I will not do it in detail, rather I will write the matrix form, what is the exact solution of the problem. This will look like this, not the exact solution, the approximate solution, 4, 6L, then 8L square, then 6L, 12L square, then 18L cube, then this is 8L square, 18L cube, then 144 by 5 L to the power 4. So this multiplied by C1, C2, C3. So since we have 3 functional, so my W approximation, W of x is C1 phi 1 plus C2 phi 2 plus C3 phi 3. Then this is equals to integral 1/3 Q0 L square, so plus 2m0, and that is 1/4 Q0 L cube plus 3m0 L, and then 1/5 Q0 L to the power 4 plus 4m0 L square. So this is my final matrix equation. So from here, if we find out C1, C2 and C3, we reach the exact solution of the problem. So you see that when I increase the order of polynomial or order of approximation or number of terms in the approximation, we slowly reaches the exact solution. Now if I just, instead of n equals to 3, if I just try to further increase the number of terms in the polynomial, that is W, if I just try to approximate like this, that C1 phi 1 plus C2 phi 2 plus C3 phi 3 plus C4 phi 4, where phi 1 is x square, phi 2 is x cube, phi 3 is x to the power 4, and phi 4 is x to the power 5. So this will not improve my solution, or rather this term will come to 0 essentially, because we have already reached the exact solution with n equals to 3. So just n greater than 3 will not improve my solution. So this is one aspect you can verify by doing this integration procedure and solving this thing. Now this completes our numerical or the example problems. Now I want to emphasize one more thing here, that we have found out how to do Rayleigh-Ritz method, but Rayleigh-Ritz method is not limited to the weak form. You can also find out the potential energy of the problem and then substitute the Rayleigh-Ritz form like this. So suppose this is my potential expression for the beam, then d2w by dx2 I can also improve this thing. So this is 0 to L m0, not m0, so this is nothing but q0 w dx, the work done, and then dw dx, and at x equals to 0, and then dw dx at x equals to L m0, so the previous problem. Now this is my potential energy. Now here I can also choose my Wx as C1 phi 1 plus C2 phi 2 and so on. So the same approximation I can substitute in the potential energy function, and then I can minimize the potential energy by choosing by minimizing this potential energy with respect to this Ritz coefficient. So del C1 phi by del C1 has to be 0, and d phi by dc2 has to be 0. If I do that, then also I will get the same coefficients what we obtained here. But obviously that choice of this has to be in this form. But this is actually will result in the same equation. So instead of doing the weak form, I can also choose the potential energy functional and minimize that potential energy function with respect to this Ritz coefficient or the constant C1 and C2. This will lead to my same solution, because we have proved that the if the bilinear form is symmetric, then we can also construct its quadratic functional, and solution with an approximating solution with the same, obviously the same approximating function for weak form as well as potential energy minimization will lead to same solution. So this is this you can check that if I do this, we'll get the same set of equation, and then we'll get the same solution that we obtained earlier via weak form. So that's all. So we'll come to we have come to end of this module. So in the next lecture will be from module 3. So thank you.